Hello, everybody. It's my pleasure to chair this Forum Numerica today. So we have Elena AGLIARI as a guest who is going to talk about the many leaves of the Hopfield model. You probably know Hopfield has been a recent Nobel Prize in physics. So Elena is a professor at Sapienza University of Rome in the math department of Castelnuovo. She got a PhD from University of Parma, and then she spent some time in Freiburg and also in Paris before joining University of Roma Sapienza. So she worked on mathematical approaches for complex systems, disordered systems, modeling in biology. And if over the years you have attended some advanced summer school or similar topics, similar events on this kind of topics, you probably saw her name and attended her talk because she's a frequent keynote at this kind of events. And it's a pleasure to have her today. So Elena, thank you for accepting this invitation.
Thank you very much, Emanuele, for this introduction, and again for the introduction and the invitation. So as you said, I will talk about the Hopfield model, which is a classical model for associative memory. And although it has been investigated in the last 40 years or even more, it still constitutes a very attractive research topic because you can enrich it and make it able to address more complex tasks while keeping it analytically trackable. And in the following, I will provide you with an introduction about this model so that even people not familiar with it can hopefully follow this seminar. And next, I will present some recent challenges involving this model, and then I will focus on a particular extension, which is referred to as Dreaming Hopfield model, and we will see that its capabilities are enhanced, but I will also show that you have to tune parameters correctly, otherwise some drawbacks may emerge. Okay, so let's start. And as I said, the Hopfield model is was originally introduced to describe associative memory tasks. Associative memory, for instance, is the task that you accomplish when you read this kind of text. I don't know if you can, you should. Okay, I see people saying yes. And in fact, we as human beings are very good at this kind of task, so good that we sometimes overdo it and we see patterns even if there aren't any. Very broadly, associative memory is the ability to reconstruct information or patterns based on some corrupted or partial cues. And depending on the context, these might also go under these names: pattern recognition or reconstruction, denoising, content addressable memory, and so on. Before going on, we should recast this kind of operation in terms that will make my mathematical treatment more feasible. So in the following, the patterns that I want to store and later reconstruct will be given by black and white pictures like this. So these are the patterns that I want to reconstruct. And you can always flatten these pictures so that they can be encoded by binary vectors. Can you see it? Okay, so I will denote by psi mu the mu-t of such vectors. They are all of length n, so entries are +1 or -1, according to whether the pixel is black or white. And I will collect them into a matrix called big psi. So the columns of this matrix are these binary vectors, and I have a k of them. So I wanted to design a machine such that it receives as input something like this and returns as output the complete flawless picture. So to this goal, I will engage n binary neurons whose state is denoted by this sigma. Okay, so they are binary and they are n, and I let them interact pairwise. I use this symbol J to denote the coupling matrix. So the entry ik of this matrix represents the strength by which neuron I and k interact together. And unless otherwise stated, it will be considered quenched, which means that it doesn't evolve in time. It is given and stays there. Instead, the neuronal configuration is let evolve according to this rule, which is biologically inspired. This local field alignment. The reason is that this I, can you see it, due to the neighboring neurons. And this one is a stochastic contribution where zeta is a random variable and t is a control parameter that I can tune so that when t is equal to 0, the dynamics is deterministic. Sigma takes the sign of the field acting on it, while when t goes to infinity, sigma is a purely random variable which inherits its stochasticity from zeta. And zeta is drawn from this distribution. It looks exotic, but in the end it's just a bell-shaped distribution centered in 0, and later I will show you why I take this. And now another point that I have to stress is that in the following, I want to build up a theory which tells us how the macroscopic behavior of this system, the emerging behavior of this system, in particular if it is able or not to accomplish this task. But I want to make these efforts for a system that is as general as possible. So what I mean is that I don't want to focus on a specific realization of these patterns. So patterns will be taken as random vectors, such that the theory that I will build is expected to hold for any sample of vectors sharing some statistical properties. And the standard choice that is made is this one. So each entry, psi I mu, is a Rademacher random variable. So it takes value +1 or -1 with the probability 1/2. So I will still retain these pictures because they help intuition, but our patterns shall be Rademacher. Another classical choice is to take the interaction matrix defined in this way. So this is named after Donald Hebb, who was a neurophysiologist, because this rule, it's a kind of mathematical translation of some empirical evidence on synaptic plasticity. So for our purposes, it is sufficient to notice that this gives rise to a symmetric interaction matrix, and it is very simple, mathematically very simple. Despite its simplicity, one can prove that if you choose this interaction matrix, then each pattern is delta epsilon stable as long as their number k is small enough and t is small enough. So what I mean with the delta epsilon stable is that if I initialize the neuronal configuration in some state at the distance delta from a target pattern, then as the dynamics goes by, the system will eventually sojourn within a distance epsilon from the target. And if epsilon is small enough, then this behavior is interpreted as a retrieval. Can you see it? Okay. Now it's time to disclose why I've chosen that particular distribution for the zeta. The reason is that you can prove that this dynamics exhibit a unique invariant distribution in the long time limit given by this distribution. You might have recognized it if you have some background in statistical mechanics. No? This is the Boltzmann-Gibbs distribution. Okay, exponential of minus beta, the inverse of the temperature, times the energy. So this quantity here plays as the energy, or as a cost function, if you prefer. Okay, so I have recast the neural network as a spin model. These sigmas can be interpreted as spins. And I can, so given this framework that I reached, I can mobilize a number of tools, concepts, ideas that have been developed within the statistical mechanics of spin models to get a description of the emerging behavior of this system. I now stress that if you take Hebb's rule for the interaction matrix, then this connection with the spin models can be made even stronger because you can take the energy function. This is written more explicitly. Maybe this is more readable. If you now plug the Hebb's rule here, then you get that this energy function is a quadratic form in terms of a macroscopic observable, M, which generalizes the magnetization of spin systems. So here M is a vector of length k, whose entry mu is given by this normalized scalar product. So M mu is measuring how well the system is retrieving pattern mu. Can you see it? So if a glance at this picture should clarify what's going on. So you have two, I'm comparing two different evolutions, say for different setups of the parameters. Same initial state, n goes by, and the evolution occurs according to this rule. Now, the green one is a successful evolution because I'm progressively retrieving the target pattern, and accordingly, the matrix magnetization is saturating to 1. While the red one is not a good one, and the matrix magnetization is vanishing. Okay, so this M is the matrix magnetization, and it plays as an order parameter that is a macroscopic quantities that tells us about the macroscopic behavior of the system, and specifically how well the system is accomplishing the task it is designed for. The last point of this introduction is to recall that, as I said, there has been a long investigation on this model, and I should mention seminal works by Amit Gutfron and Sompolinsky, who were able to summarize the behavior of the systems in terms of a phase diagram. You're probably familiar with the concept of the phase diagram, like the one of the water, which tells you if you're ice, water, or vapor, okay? So this is the analogous for the Hopfield model. So they realized that the macroscopic behavior qualitatively depends on two parameters. One is T, that we have already seen. The other is alpha. Alpha is defined here, and it is named load, because it is the ratio between the number of patterns that I want to store and the amount of resources that I'm employing. And so when T is large, noise in the dynamics prevails, and neurons are behaving randomly. This is an ergodic phase, not interesting to our purposes. We should set T, both T and alpha, small enough in order to be in this blue region where patterns are minima in the energy landscape. So they are stable configurations. In this region, this behavior occurs. While in this red region, which is a so-called glassy phase, patterns configuration are no longer minima. So this is not interesting for us. And notice that we have a largest load affordable, which is roughly 0.138, which means that we can store a number of patterns which at most grows linearly with n. We have a precise scaling. Okay, now I will discuss some recent challenges involving the Hopfield model.
Why is it important? The patterns are far enough from each other that there's no...
Pardon, say it again?
Why is it important that you have the Rademacher distribution?
Can you repeat the question for the audience online? 1 second, you can repeat the question.
Why did you have to use the Rademacher distribution?
Yeah, this is an important point. One answer, a very simple answer, is that in this way you can enjoy the fact that the scalar product between two patterns is vanishing with n. And this simplifies a lot your calculations. So correlation between patterns are relatively small. And this is important because it is precisely the correlation between patterns we start to be relatively large when alpha is large, which prevents you to correctly retrieve, because then you start to overlap them. So what's going on here is analogous to what happens when I ask you to memorize some, say, telephone numbers. Okay, this is an old-fashioned example, but I can manage with a few of them, but if they are a lot, I start to mix them up. And this is what happened here. And also it is fundamental to have them IID. Okay, thank you. And now some recent applications. So one very interesting research line is employing the Hopfield model as a model for so-called content addressable memory. And you have this kind of phenomenology emerging in different kind of systems, for instance, in biology. Then here the point is to interpret the interacting units according to the application you have in mind. I make you an example. You might, for instance, look at units as immune cells. So retrieval, in that case, corresponds to the development of an immune response when an antigen arrives and the antigen was previously seen, so that you have memory in your host body of that antigen. Or another very interesting research line is about the embedding topology. So you can allow neurons to interact in groups of 2, 3, or more. So you have an hypergraph, and this multi-connection makes the system able to afford higher load. In this case, the number of patterns that you can store can grow superlinearly with respect to n. And this is a well-known fact since the 80s, but more recently, these so-called dense associative memories have been shown to be robust against, for instance, adversarial attacks, or to cope with noise affecting the interaction matrix. Also, they can be related to transformers, which form the architecture of large language models. So it is a very active research line. And I also would like to mention at a bridge between the Hopfield model and Boltzmann machines. So Boltzmann machines are in turn paradigmatic model in machine learning, and this equivalence, which I will later explain in more details, allows you to translate the knowledge available for the Hopfield model, for which you have a long tradition, to the realm of machine learning. So, for instance, based on this knowledge, you can figure out which is an optimal setup for hyperparameters according to your training dataset, or figure out a good choice for the activation function of your neurons, or find a way for pre-training weights so that training is much faster. And the equivalence is based on a simple Gaussian integral. So here you have the Hopfield model, and here a Boltzmann machine where the visible layer is made of n binary neurons, and the hidden layer is made of k Gaussian neurons. Now, if you set the weight matrix here according to this relation, so big Xi is the matrix of your patterns, then you can show that the two partition functions are the same. And the partition function basically control the emerging behavior of the system. I mentioned this equivalence because there is a nice interpretation from the biological side. I don't know if you have ever heard about the grandmother cell theory. Maybe not. Well, according to this theory, which is debatable, but I just tell you what it implies. Our brain is featuring neurons which are hyper-specialized. That is, that they get active when in the presence of stimulus which is very specific, like grandmother. And in this context, we have a structure which is reminiscent of that theory, because based on this equivalence, you have that hidden neurons play as a hyper-specialized neuron, meaning that this guy here get active only when the visible layer is retrieving or generating, according to the task, the pattern labeled 1. Okay, say if the pattern labeled as 1 represents the grandmother, then the neuron corresponding to the grandmother gets active while the other remain quiescent. And by the way, you don't need to know to set up this condition at the beginning. This equivalence can also be obtained as a fixed point of a learning routine. So you don't know to have this in advance. Okay, now let us focus on a particular extension of the Hopfield model. So this time we are not concerned about the underlying topology or the interpretation of units. This time is about the interaction matrix, how it is defined. In other words, I want to revise Hebb's rule. So let's resume this phase diagram, and let me stress that this shape of the phase diagram depends on the choice of the interaction matrix. If you change the interaction matrix, you expect a different behavior. And in particular, the existence of this threshold here, which is sharp, it is an abrupt phase transition here, is not optimal. In other words, one can prove that there exist other choices for the interaction matrix such that the critical load is 1. So in principle, this blue region could reach alpha equal to 1, which would be a great gain, because I would be able to retrieve a larger amount of patterns with the same amount of resources. It is easy, relatively easy, to find a coupling which reaches that threshold. This is given by the so-called cohonent projection matrix, whose definition is given here. This is a projector on the space of patterns of the vector Xi. So this means that if I apply this to a pattern, this is left unchanged. And so this implies that each pattern is stable. Okay. There are other rules which try to improve the performance of the network, and now I'm presenting one which is again inspired by biology, and in particular by the mechanisms occurring in mammals' brain during sleep. So during sleep, you have an alternation of different phases, in particular a slow wave phase, where the sleep is deep, heartbeat are slow, and a rapid eye movement phase during which you are dreaming. And there occur mechanisms in these phases which yield to a consolidation and a remotion, respectively, of memories collected during the day, for instance. So there is a kind of defrag occurring now in your brain during sleep. And we tried to mimic these mechanisms, and we implemented this evolutionary rule for the interaction matrix. So you see two contributions. The pink one mimics the consolidation, and the green one the remotion. Now, I do not have time to explain why they should look like that, but I give you an explanation, say, a posteriori. You can translate this discrete time equation into a continuous time differential equation, and this is the solution. So T is the time, the continuous time, which we will call a sleeping time. And the pink contribution is responsible for the numerator, the green one for the denominator. And you see that the numerator brings to a consolidation. It corresponds to lowering T, the temperature, while this one brings to a remotion. Why is that? Because you can see that if you look at the two limiting cases, when T goes to 0, you recover Hebb's rule. But when T goes to infinity, you recover Cohen's rule. So when T goes to infinity, you are sharpening your minima such that there is no longer overlap between them. So you are basically reshaping your energy landscape, reducing the overlap between them, as if the patterns were perfectly orthogonal each other. If you're not convinced by this, I can give you another point of view. So you can look at the spectrum of the interaction matrix and how this varies as we tune the sleeping time. So at the beginning, you have a Marchenko-Pastur law for the spectrum. And as time goes by, this distribution progressively peaks at lambda equal to 1. In the end, you have a delta, which corresponds to the projector. But one can prove that in this process, the eigenspace are stable. So as your spectrum is collapsing on a delta, the likelihood for a configuration that is not a pattern to be stable, to be left unchanged by the application of the operator J, is vanishing. Okay, so you must be a pattern in order to be stable as T goes by. Now we can plug the revised matrix J into the energy function and apply statistical mechanics tools to get a phase diagram, ideally, so to get a description of the emerging behavior. Here, the standard pathway is to look for an explicit expression for the free energy. An explanation for that is that the free energy plays as a cumulant generating function. So if you get this expression, then by simply deriving this quantity, you can get an estimate for the expectation of observables like the Mattis magnetization. Okay, so if you get it, then it's a matter of deriving to get the observable that allows you to draw the phase diagram. Unfortunately, getting such an explicit expression is quite challenging. One can do that under some simplifying assumption like replica symmetry, but you have several tools that you can leverage to get this quantity. For instance, a replica trick. I don't know if you have ever heard about that, or interpolation method, or large deviation based tools. Usually you get the so-called quenched free energy, meaning that you are averaging over the realization of patterns, and you're doing it in the thermodynamic limit. So when the number of neurons is very large. The reason is that you want to enjoy the law of large numbers and so on. So I will not bother you with the details and directly give you the phase diagram. So you can see the beneficial role of sleep, because as the sleeping time gets larger and larger, this nasty, glassy region progressively collapses onto the horizontal axis, and you're left with a wide blue region, and here you are retrieving. And you also reach the theoretical upper bound, alpha equal to 1. So nice, and even more, you can get for this model the equivalent Boltzmann machine. So the difference now is that in order to accommodate this extra term, you have to include connections among hidden neurons. You have intralayer connection. And these are very well interpretable because they are inhibiting a connection, meaning that they unfavor the simultaneous activation of hidden neurons. And their strength is large when the pattern, say for Z1 and Z2, so pattern Xi1 and Xi2 are correlated. So the higher the correlation, the stronger this interaction, which is of inhibiting sign. So in other words, these additional links inhibit the emergence of this kind of hallucination or spurious states. So the concept of grandmother and house are correlated. So without these additional links, there is a high chance of generating this kind of spurious states. But having this connection, I have a strong inhibition between this one and this one. So their simultaneous activation is unfavored. Yes.
Is this related to winner takes all?
So we can repeat the question.
Is this related to winner take all?
There is not precisely that mechanism. It's more about the fact that the energy is lower when this guy and this guy are not simultaneously active. But for instance, as there is not such a big correlation between, say, the watch and the grandmother, this connection might be not that strong. So, this connection is not that strong, but since the pattern encoded in these links does not favor the simultaneous activation of this, there is not even need for that link. So it's, I don't know if it can be connected with winner take all. There is not a reinforcement, a progressive reinforcement. It is just a matter of energy minimization or cost energy minimization. I don't know if this is what you had in mind. And
it sounds, yeah, it sounds to me like this. You
you're trying to avoid that multiple of the neurons on the right-hand side are active, right? Firing.
Because if you have a multiple activation, then this would make spurious states like this emerge on that side, which means that if you're using this machine for generation tasks, then you're not generating patterns reminiscent of grandmothers only, but mixture between that.
Okay, thank you.
I think. Okay, now I move on, and I want to address a more realistic setting. So I will relax the hypothesis that these patterns are accessible. So these patterns, psi mu, are now ideal patterns, not accessible. Instead, I can access to empirical realization of these patterns like this, which are noisy realizations. So these psi tilde are noisy versions of these ideal patterns that are out of reach. So my data set now is made of m examples for each pattern. And again, since I wanted to keep the model analytically trackable, I will define these examples in some controllable way. Specifically, I will introduce a flipping probability for pixels. So I will ask to each pixel, do you want to flip or not? And this can be written in this way. And so in practice, I have an additional parameter, R, which controls the quality of the dataset. So when R is equal to 1, then each example is a perfect copy of the archetype, while when R is equal to 0, my dataset is a mess, because each example is in the average orthogonal to the related archetype. I now have these datasets, and I want to build up an interaction matrix based on that. And I can envisage two ways according to whether the label mu is disclosed or not. So suppose that you have a teacher which discloses the label mu. So I can group examples label-wise, and then a reasonable way to proceed is to replace the archetype with the empirical average made over examples for each group. So it is now very simple to proceed, because I replace the original dataset with this bar psi, where each column is the empirical average corresponding to that class. And then Hebb's rule is straightforwardly revised. It's again the product between bar psi and bar psi. If the teacher is not available and the label mu remains veiled, then I have these examples which are all mixed up together. Okay, without any prejudice, I simply take as dataset a matrix, big psi tilde, where each column is a single item of my dataset. So now this matrix psi tilde will be of size n times mk, because I have mk single examples. And again, I can revise Hebb's rule straightforwardly. That's it. And I can also revise the interaction matrix with the sleeping mechanism by simply replacing psi with psi bar or psi tilde. That's it. Okay, everything is very natural. Notice that here the pattern correlation matrix is between the empirical averages, while here is between the single example. So C tilde will display a blockish form structure. Okay, let's see what's another thing that I should mention is that Notice that here I'm not starting from the examples, sorry, I'm not starting with the patterns that I want to retrieve. I'm starting with either bar xi or tilde xi. But still, I'm interested in the ability of the system to reconstruct the archetype. So in this sense, the task is a generalization kind of task. So I will start by showing you what happens in the supervised case, so when we have the label. Now, our parameters are, again, big T, that is the noise affecting the dynamics, alpha, the load, and small t, that is the sleep time. And then I have two additional parameters stemming from the dataset, M, the size of the dataset, and R, the quality of the dataset. But we are lucky because M and R just appears under this combination. So I have a unique parameter, rho, which can be seen as the dataset entropy. Okay. And here is how the phase diagram is reshaped as a function of the sleeping time and as rho. So when rho is equal to 0, you have the phase diagram as the classical case, because rho equal to 0, for instance, means that R is equal to 1. So the empirical average are the archetypes. But when rho gets larger and larger, this retrieval region is progressively smaller and smaller. This is quite intuitive. Okay? Your data set gets more and more noisy, so your ability to reconstruct the archetype is lowered. But still, sleep has a beneficial role, as you can see. And we can leverage this, because suppose that your load is 0.1 and your data set is not that good, it displays rho equal to 0.15. So you are here and you are outside your retrieval region, which is this light blue here. You're outside, so you cannot use your machine. You have two options to reduce rho. You can collect more dataset, or you denoise them somehow. If you can do that, and you can reduce the entropy to 0.05, then you would be inside the retrieval region and you're happy. But there is another option, that is, you can rise T, for instance, up to 5, and then you would be perfectly within the retrieval region without consuming energy or time to collect new data. So this is potentially quite interesting, but the natural question is this an effect due to the very simple and structureless dataset? So we checked it on some benchmark datasets, like the MNIST, Fashion NIST, and the Olivetti dataset. And in each case, we compare the two scenarios. The green one, where the sleeping time is small and you have a lot of data, and the red one, where the sleeping time is large and you have only few data. And as you can see, the latter is always overperforming the former. Okay, so if you leverage this sleeping mechanism, you can make it with just a few examples. But now, another natural question arises. Well, why you keep this parameter t, and why don't you simply put t equal to infinity, which would also the effect of getting rid of one parameter? So why not putting directly t equal to infinity? Unfortunately, if you oversleep, there are some drawbacks. And here is an intuitive idea for why we can't sleep too much. So we start from k times m examples, xi tilde, okay, which are some noisy version of archetypes. And this is a picture of the energy landscape from above, and this is a kind of cross-section, just to give you an idea. This is a cartoon picture. But if K is large, here different examples corresponding to different labels are depicted in different colors, and they are very overlapped each other. So that if you start somewhere here, so if your input is somewhere here, so you might end up in some local minimum corresponding to a mixture between different examples of different archetypes. So it is a very messy situation. But if you now switch the sleeping time on, you are reshaping your energy landscape and making your minima sharper, reducing the correlation between your minima. And the correlation that are first ruled out are the weakest one, namely the inter-cluster correlation. So you are reaching a situation like this, which is very convenient, because if I now start somewhere here, then I will end up somewhere kind of a center of mass of this cluster of minima. But now, if you oversleep, then you will start to reduce even intra-class correlation, and you are disentangling the single examples. So basically, you are now retrieving the single example. So you are overfitting. You are retrieving the example along with the error, the noise it is affected by. To convince you about this picture, I can show you a learning perspective on this problem. So you have this training data set, and you want to design a J such that this stability criterion is fulfilled. Now I'm using this shorthand notation, L, to denote mu and A. So mu is the label for the archetype, and A is the label within each cluster. You introduce, for instance, a mean square error cost function, where you ask for the symmetry, and you also introduce regularization. So you know that regularization usually is introduced to avoid overfitting. You can implement a gradient descent over this cost function, and the solution is given by this. Maybe it doesn't tell you too much, but if you have memorized J tilde in the previous slides, you will see that if you set the inverse of the regularization parameter equal to t, the sleeping time, then you have recovered the J tilde. So the sleeping time plays as the inverse of the regularization parameter. So if t goes to infinity, you have no regularization, and you are at risk of overfitting. And here are some numerical experiments showing the error in the generalization versus this quantity, such that when you are close to 1, t goes to infinity. And you see that the performance is not monotonic. When t is too large, then the error starts to grow again. And the last point to convince you about that is, again, based on spectral tools to inspect the structure of the interaction matrix. So now, again, I want to show how the spectrum of the interaction matrix depends on T. Unfortunately, the calculations now are a bit more tricky, because I have no longer this as a starting coupling matrix, but I have this. And this has no longer a V-chart-like structure, because you have correlation within the columns of this matrix. But you have some more sophisticated tools to get the spectrum of that matrix. And it is interesting to see how this spectrum depends on R. Again, R is the quality of the dataset. You see that at a certain point, the spectrum split into two components, one corresponding to large eigenvalues and one corresponding to small eigenvalues. And this bulk, the eigenspace corresponding to this bulk is the one spanned by archetypes. And so it is this splitting, therefore, has some positive consequences, because if you think of your starting configuration, sigma 0, then you apply the dynamics at 0t, for instance, and the effect of this j tilde is, when you have this splitting, is to amplify the contribution of sigma 0 that belongs to the space spanned by archetypes and to shrink the other contribution. So you are progressively moving closer to the archetype. And here is a corroboration of what I said. This dashed line corresponds to the emergence of this splitting in the spectrum, while the color map is the generalization ability. So this dark region is where the system generalizes well. It can retrieve the archetype. And so the emergence of the splitting is a necessary condition for this nice capacity. So on top of this now, I let the network sleep. So I apply the sleeping mechanism. And we know how the spectrum is reshaped due to the lemma that I showed you before. And we expect that the effect is particularly positive when these two bulks are well separated. So here is the distance between the two bulks, and you see a non-monotonic behavior. And in fact, this is mirrored by the performance of the network. You see that at intermediate sleeping time, you saturate these regions. So this is the setting where you can generalize very well, even for a data set which is not particularly big or particularly good in quality. Okay, so that's all. And I, of course, thank you for your attention, and also all the people who contributed to these works. Thank you so much.